Hi, my name is Yuri Chichulin. I am a senior physician at Advanced Analytics Branch with Workplace Safety Insurance Board of Ontario for the past 5 years. My primary interests are predictive and causal statistical modeling and data science. I am a SAS user for more than 18 years. I am sitting on executive committee for SAS Health User Group in Toronto and 10 Canadian SAS Virtual Health User Groups. Today, I'll be talking about the work that we did on reliability of individual predictions estimation for claim risk scoring models. Standard methods for assessing predictive model accuracy estimate the overall predictive power of a given model averaged across all test observations. Those metrics would be accuracy, sensitivity, specificity, C-statistics, mean squared errors, and other metrics. Although these estimates evaluate model performance by summarizing the error contributions of all test examples, they provide no local information about the expected error of an individual prediction. Even if a model is very accurate on average across all observations, it doesn't mean that individual predictions are of the same reliability across all the data. We can broadly define reliability as correctness of each individual prediction. Individual prediction reliability estimates can be directly shown to users to help them gauge whether they should trust the artificial intelligence system or not. This is very crucial when models' predictions influence important decisions such as medical diagnosis or injured worker return to work plan development. If individual prediction reliability is low, a physician may utilize other available methods to derive a care plan for this patient. The same is true in worker compensation settings. If an individual prediction for a given injured worker has low reliability, default actions suggested by a given predictive model, such as triage into high versus low risk group, could be ignored, and additional human interventions could be taken to collect additional data and develop an appropriate return to work plan. There are two broad classes of approaches for estimating the reliability of individual predictions. The first one is model-dependent methods, and they usually report prediction confidence intervals that are generally calculated via least squares estimation or by estimating the uncertainty in learned model parameters. The drawback of these approaches is that they mandate the use of a particular type of classifier. So if we develop confidence interval for logistic regression, then we have to use logistic regression, and those methods will be very specific to this particular method. The second approach is model-independent approach, and most model-independent approaches involve retraining the predictive model using an enhanced data set that contains the original training set supplemented with new unclassified data examples where class labels for the unlabeled data are assigned based on the model's predictions. The model performance before and after retraining is used to estimate reliability of predicted classes for the new data. Model-independent approaches can be used with a variety of different models and methods, irrespective of the approach used to develop or train a given predictive model. In this particular work, we test reliability of individual predictions estimation for two example predictive models. Example 1 is a claim segmentation model. This model predicts probability of being on loss of earnings benefits at 3 months duration from accident date. This is a binary outcome model estimated using a random forest. Example 2 is case-based reserve model. This model predicts expected duration on LA benefits up to 12 months duration. And this is a discrete time trial analysis model. We use a model-independent approach, and we retrain the predictive model using an enhanced data set that contains the original training set supplemented with new unclassified data examples, where class labels for the labeled data are assigned based on the model's predictions, and then we evaluate the difference between the two estimated probabilities for each individual prediction. So once we train the two models, we calculate the reliability metric as the absolute difference between the two predictions for each individual prediction. We do evaluation of reliability metric on a test data, which is unseen data. This data wasn't seen by any of the models that we trained. And we also use stratified duration outcome flag sampling to create training set and test data sets so that we can preserve the same prevalence of the duration outcome as in the original data in both training and test samples. This slide shows a diagram of how this method works in detail. So basically, we have all available data, which we split into modeling data and test data, which we don't touch with any of our models. The modeling data we split further into two samples, sample 1 and sample 2. In our particular approach, we used a split 60-40. So we used 60% of data in sample 1 and 40% of data in sample 2. Then we train our initial reliability model on sample 1. And once we have this model, we score sample 2 using this initial reliability model so that we can assign outcome labels to this data. So basically for this sample 2, we assume that we don't know the outcome, and we just score this data with our initial reliability model so that we can assign those outcome labels. Then we combine the two data sets, and we train second reliability model on this combined data. So once we have these two reliability models, we go to our test unseen data, which wasn't touched by any of our modeling, or it can be just live production scoring model. So like we can go into production and it can start scoring data. So our approach for test data example and production data would be the same. So we score all test data using initial reliability model, and we calculate y1 probability 1. Then we score all test data using second reliability model, and we calculate prediction 2. Then we calculate unreliability metric for each individual prediction as an absolute difference between the two probabilities. This is in a nutshell how the method works. Now we're showing some results of this approach. First, this is example 1 for binary outcome model, which is estimated using random forest. Here we have a histogram of unreliability metric. And as you can see, the unreliability metric, which is the difference between the two probabilities, if you recall, is right skewed. So we have heavy tail on the right. We also have a scatter plot of unreliability metric versus probability. And as you can see, observations are concentrated mostly around uncertain probability region, in the middle of the probability range, or it's pretty much the prevalence of the outcome in the data. So which is kind of expected, because we would expect that we will have more unreliable predictions around uncertainty probability region. If we move further to the ROC curves, we built 3 ROC curves. The first ROC curve is for the main full model. The second ROC curve is for reliable predictions, where unreliable flag is 0. And the third ROC curve is for predictions which are flagged as unreliable. So unreliable flag is 1. And as you can see, ROC curves and statistics for reliable observations is very close to that of the main full model. So ROC for reliable observations is very close to that for the full model. And statistics is also very close. We can see substantial deterioration in ROC and statistics for observations identified as unreliable. And as you can see, statistics is close to 0.5, which is random choice. And ROC curves also shows that there is substantial deterioration in predictive accuracy. So we can, from that, we can say that for our example 1 binary model, the reliability estimation works very well. We can also build calibration curves. And here I'm showing calibration curves for reliable observations and observations that are defined as unreliable predictions. And basically, if the expected and observed curves coincide, then we can say that calibration is very good. And if they depart from each other, then calibration is not very good. And as you can see, we have very good calibration on reliable predictions, and calibration for observations defined as unreliable predictions is quite poor. Moving to example 2, here we'll be talking about restricted mean survival time discrete time historal analysis model. So it's a different type of modeling approach, but as I said, because we use model independent method, we can apply it to any kind of classifier or method for modeling. Again, histogram of unreliability metric shows that distribution of unreliability metric is heavily skewed. And again, a scatter plot of unreliability metric versus probability shows that observations are concentrated mainly around uncertainty probability region, in the middle of the probability range. So again, this is expected, and it shows that our method produces meaningful expected results. Here we have ROC curves again for our full model, for reliable observations and unreliable observations. And again, we can see that ROC curve for reliable observations is very close to that of the full model. And actually, if you can look into the statistics, C-statistic is actually better for reliable observations than it is for overall model. So we can say that we kind of improve our model by removing unreliable observations. And ROC curve for unreliable observations shows very poor calibration, which again shows that our method works well. Here we show calibration curves for reliable observations and unreliable observations, and again, calibration for reliable observations is quite good. The expected line shows follows observed line very closely, and here observed line departs from expected line quite a bit. So again, we can show that we did find those areas in our data that are not as good calibrated as the rest of the data using this unreliability method. In terms of the discussion, we can mention that the Claude approach allows identification of individual predictions with low reliability. It does a remarkably good job of separating reliable from unreliable individual predictions based on ROC curves, statistics, and calibration curves calculated on the test and seen data. And as we showed, statistics for reliable prediction is the same or even better than for a full model, which makes the resulting model relatively more accurate on the remaining trusted individual predictions. And it is very close to random choice, which is statistically close to 0.5, for predictions identified as unreliable. Calibration curves for predictions identified as unreliable also show poor calibration. We arbitrarily use top third percentile of reliability metric distribution to flag individual predictions as unreliable, and this cutoff could be increased or decreased based on the required sensitivity of a given risk prediction model and the availability of resources for intense human follow-up intervention on predictions identified as unreliable. So we can flag more predictions as reliable or less, depending on our capacity to handle those predictions or on a particular operational needs. Identification of low reliability for individual predictions for claim-based scoring models may help to avoid automatic action based on artificial intelligence prediction for unreliable subgroups of predictions and trigger an in-depth human intervention in additional data collection and development of an appropriate return to work flag. So this concludes my presentation, and I would like to thank you for listening to it.